Hello and welcome to the Tech Think Tank. We're back with the second video in our Amazon Web Services series. Today, we'll be taking a deep dive into the world of AWS compute resources. AWS provides a plethora of options when it comes to computing, making it a popular choice for businesses of all sizes. In this video, we'll be exploring some of the most widely used AWS compute services such as EC2, ECS, ECR, Elastic Container Service for Kubernetes, AWS Elastic Beanstalk, AWS Batch, and Amazon Light Sale. If you're new to AWS or just looking to expand your knowledge of compute resources, you've come to the right place. So grab a cup of coffee, sit back, and join us on this journey into the world of AWS compute. And of course, if you haven't seen episode 1 of the AWS series, I'll recommend you to see that. Please click the pop-up banner now or the link in the description below to watch episode 1. Welcome to this detailed lecture on compute in AWS. Before we dive into compute services, resources, and features, let's define what compute means. In simple terms, compute resources are the brains and processing power required by applications and systems to perform computational tasks through a series of instructions. It's closely related to common server components, such as CPUs and RAM, found in physical servers within data centers. AWS offers various services and features that provide compute power for different functions. For instance, some services utilize hundreds of EC2 instances or virtual servers to process millions of instructions continuously for months or even years, while others may only need a few hundred milliseconds of compute resource to execute a few lines of code within AWS Lambda. Compute resources are consumed in different quantities, for different durations, across different categories, offering a wide range of performance and benefit options. To help you decide which compute resource to use in AWS, there's a Cloud Compute Index available that showcases various examples and scenarios of where different compute deployment units can be utilized. This concludes our brief lecture on compute in AWS. Let's now explore some of the services offered by AWS that provide this compute resource, beginning with Elastic Cloud Compute, EC2. Let me explain what EC2 is and how it works. EC2 is a computing service that enables you to deploy virtual servers within your AWS environment. It is one of the most popular services used in AWS, and as such, I'll focus on it in greater detail than the other services offered by AWS. When creating your EC2 instance, there are several elements to consider. These include Amazon Machine Images, AMIs, Instance Types, Instance Purchasing Options, Tenancy, User Data, Storage Options, and Security. Let's start by discussing AMIs. An Amazon Machine Image is essentially a preconfigured template of an EC2 instance that allows you to launch a new EC2 instance quickly. AMIs come with an operating system and pre-installed applications, as well as any custom configurations you may have made. AWS provides a wide range of AMIs covering different operating systems, including Linux, Red Hat, and Microsoft Windows. You can select an AWS-managed AMI or create your own custom AMI to speed up deployment. For example, suppose you start with an AWS Linux Server AMI and install custom applications and configurations. In that case, you can create a custom AMI or template of that instance, including all your configurations and custom applications. When you need another server with the same functionality, you can select your custom AMI as the base image, and the instance will launch with Linux Server, your custom applications, and configurations pre-installed. This process is beneficial when implementing auto-scaling. You can also choose AMIs from the AWS Marketplace, which is an online store offering trusted vendor AMIs, including those from Cisco, Citrix, and Alert Logic, among others. These AMIs may have specific applications and configurations already in place, such as built-in security and monitoring tools or database migration systems. Additionally, community AMIs are available, which are created and shared by other AWS members. Let's take a closer look at the different types of instances available on Amazon Web Services, AWS. After you've selected your Amazon Machine Image, AMI, from one of the sources we previously discussed, the next step is to choose an instance type. An instance type determines the size of your instance based on a variety of parameters, including ECUs, EC2 compute units, vCPUs, the number of virtual CPUs on the instance, physical processor, clock speed in gigahertz, memory, instance storage capacity, and whether or not it supports EBS-optimized storage. Network performance and support for IPv6, process architecture, AESNI, AVX, and Turbo are also key factors to consider. For general usage of an EC2 instance, the primary parameters to be aware of are vCPUs, memory, instance storage, and network performance. However, the ideal instance type depends on your particular application and usage. AWS offers a wide variety of instance types, allowing you to select the most appropriate instance for your needs. Instance types are grouped into different family types that offer distinct performance benefits. Within each family, you'll find a range of instance types with varying CPU, memory, storage, and network performance. The various instance families include 1. Micro-instances, which have minimal CPU and memory power, and are ideal for low-traffic websites and other low-throughput use cases. 2. General-purpose instances, which offer a balanced mix of CPU, memory, and storage and are well-suited for small to medium databases, test and development servers, and back-end servers. 3. Compute-optimized instances, which are designed for high-performance front-end servers, web servers, high-performance science and engineering applications, and video encoding and batch processing. 4. GPU instances, which are optimized for graphic-intensive applications. 5. FPGA instances, which allow you to customize field-programmable gate arrays for application-specific hardware accelerations. 6. Memory-optimized instances, which are primarily used for large-scale enterprise-class in-memory applications, and are also ideal for enterprise applications such as Microsoft SharePoint. 7. Storage-optimized instances, which are optimized for enhanced storage and are great for analytic workloads, NoSQL databases, data file systems, and log processing applications. By selecting the most appropriate instance type for your needs, you can achieve optimal performance within your applications. EC2 instances can be purchased through various payment plans designed to help you save costs by selecting the most appropriate option for your deployment. Familiarizing yourself with these options can result in significant savings depending on your use case. The following are the different EC2 payment options. 1. On-demand instances. These are EC2 instances that can be launched at any time and provisioned within minutes. They are ideal for short-term uses, where workloads are irregular or can be interrupted. You pay a flat rate based on the instance type selected, and it's charged by the second. Many AWS users use on-demand instances in testing and development environments. When you stop or terminate your on-demand instance, you stop paying for the compute resource. 2. Reserved instances. These allow you to purchase a discount for an instance type with set criteria for a set period of time in return for a reduced cost compared to on-demand instances. This reduction can be as much as 75%. These reservations must be purchased in either 1 or 3-year time frames. You can achieve further reductions with reserved instances, depending on which payment method you select. There are 3 options available: all upfront, partial upfront, and no upfront. Reserved instances are suitable for long-term, predictable workloads, allowing you to fully utilize the cost savings offered by EC2. 3. Scheduled instances. These are similar to reserved instances, but you pay for reservations on a recurring schedule, daily, weekly, or monthly. For example, you might have a weekly task that performs some kind of bulk processing for a few hours at the same time every week. With scheduled instances, you can set up an instance to run during that set timeframe once a week, saving you the cost of using on-demand instances. Note that even if you don't use the instance, you will still be charged. This option is suitable for scheduled workloads that are not continuously running, whereas a reserved instance would be preferred for continuous workloads. 4. Spot instances. These allow you to bid for unused EC2 compute resources, but the resource is not guaranteed for a fixed period. To use spot instances, you must bid higher than the current spot price set by AWS, which fluctuates depending on supply and demand of the unused resource. If your bid price is higher than the spot price, you'll purchase that instance. But as soon as your bid price becomes lower than the spot price, you'll receive a 2-minute warning before the instance automatically terminates and is removed from your AWS environment. The advantage of spot instances is that you can bid for large EC2 instances at a low cost, saving you a significant amount. However, spot instances are only useful for processing data and applications that can be suddenly interrupted, such as batch jobs and background processing of data. 5. Capacity reservations. These allow you to reserve capacity for your EC2 instances based on different attributes such as instance type, platform, and tenancy, within a specific availability zone for any period. This ensures that you always have the available number of instances you require within a specific availability zone immediately. You can use capacity reservations in conjunction with your reserved instances discount to provide additional savings. Let's now delve into EC2 Tenancy, which refers to the underlying host where your EC2 instance will reside, i.e., the physical server in an AWS data center. AWS offers different options with pros and cons to each. Shared tenancy allows your EC2 instance to launch on any available host that meets the specified resources required for the instance type. Your instance shares the host with other customers and users who have EC2 instances running on the same host. AWS implements advanced security mechanisms that prevent one EC2 instance from accessing another on the same host. Dedicated tenancy includes dedicated instances and dedicated hosts. Dedicated instances are hosted on hardware that no other customer can access, and only your AWS account can access them. You may need to launch dedicated instances due to internal security policies or external compliance controls. However, dedicated instances incur additional charges since you are preventing other customers from running EC2 instances on the same hardware, leading to unused capacity remaining. Nevertheless, other resources you have running in your own account might still share the same hardware. Dedicated hosts offer additional visibility and control over how you place your instances on the physical host. They also allow you to use your existing licenses, such as PAVM or Windows Server licenses. Using dedicated hosts gives you the ability to launch multiple instances on the same host and align with any compliance and regulatory requirements. Unless you need to address any compliance or security issues that require dedicated tenancy, I recommend using shared tenancy to reduce overall costs. During the configuration of your EC2 instance, there is a section called User Data, which allows you to enter commands that will run during the first boot cycle of the instance. This is a great way to automatically perform functions upon boot, such as pulling down additional software from software repositories or downloading the latest OS updates. For example, you could enter yum update y for a Linux instance, which updates the instance software automatically during boot. As part of the EC2 instance configuration, you are asked to select and configure your storage requirements. Selecting storage for your EC2 instance depends on the instance type, what you intend to use the instance for, and how critical the data is. Storage for EC2 can be classified into two distinct categories: persistent and ephemeral storage. Persistent storage is available by attaching elastic block storage, EBS, volumes. Ephemeral storage is created by some EC2 instances themselves using local storage on the underlying host, known as instance-backed storage. EBS volumes are separate devices from the EC2 instance itself, and are network-attached storage devices that are logically attached to the EC2 instance via the AWS network. The data on EBS volumes is automatically replicated to other EBS volumes within the same availability zone for resiliency, which AWS manages. You can disconnect an EBS volume from your EC2 instance, and the data will remain intact, allowing you to reattach it to another EC2 instance if required. You can also implement encryption on these volumes if needed and take backup snapshots of all the data on the volume to S3. EBS volumes can be created in different sizes, with different performance capabilities, depending on your requirements. Ephemeral storage or instance-backed storage is physically attached to the underlying host on which the EC2 instance resides. AWS EC2 instance's data saved on ephemeral storage is lost as soon as the instance is stopped or terminated. If you reboot the instance, the data will remain, but not if you stop it. Therefore, if you need to retain data, it is not recommended to use instance-backed storage for this data. Instead, use EBS volumes. With the main elements of the EC2 service covered, you should be equipped to create your first EC2 instance and choose the optimal configuration to suit your requirements. We hope this information helps you get started on your EC2 journey. Up next, I will give you a high-level overview of Amazon EC2 Container Service, or Amazon ECS. This service allows you to run Docker-enabled applications packaged as containers across a cluster of EC2 instances without having to manage a complex and administratively heavy cluster management system. Amazon ECS abstracts the burden of managing your own cluster management system by passing that responsibility over to AWS, specifically through the use of AWS Fargate. If you're unfamiliar with Docker, containers, and AWS Fargate, let me quickly define them. AWS Fargate is an engine that enables ECS to run containers without having to manage and provision instances and clusters for containers. Docker is a piece of software that automates the installation and distribution of applications inside Linux containers. If you want to know more about Docker, click the pop-up banner now or the link in the description below. A container holds everything that an application requires to run from within its isolated container package, such as system libraries, code, system tools, and runtime. Containers are decoupled from the underlying operating system, making them portable, lightweight, flexible, and scalable across a cloud environment. With Amazon ECS, your existing containerized applications packaged locally will work seamlessly. The service removes the need for you to manage your own cluster management system, thanks to its interactions with AWS Fargate. There is no need to install any management or monitoring software for your cluster because the service takes care of everything, allowing you to focus on building great applications and deploying them across your scalable cluster. When launching your ECS cluster, you have the option of two different deployment models, a Fargate launch and an EC2 launch. The Fargate launch requires less configuration and only requires you to specify the CPU and memory required, define the networking and IAM policies, and package your applications into containers. With an EC2 launch, you have a greater scope of customization and configurable parameters. For example, you are responsible for patching and scaling your instances, and you can specify which instance types to use and how many containers should be in a cluster. Monitoring is taken care of through the use of AWS CloudWatch, which will monitor metrics against your containers and your cluster. You can easily create alarms based on these metrics, providing you with notification of specific events such as your cluster size scaling up or down. An Amazon ECS cluster is made up of a collection of EC2 instances, so you can use some of the functionality and features discussed in this course, such as security groups to implement instance-level security at a port and protocol level, elastic load balancing, and auto-scaling. The clusters themselves act as a resource pool, aggregating resources such as CPU and memory. The cluster is dynamically scalable, meaning you can start your cluster as a single small instance, but it can dynamically scale to thousands of larger instances. Multiple instance types can be used within the cluster if required. Although the cluster is dynamically scalable, it can only scale within a single region. Amazon ECS is region-specific, so it can span multiple availability zones, but it cannot span multiple regions. You can schedule your containers to be deployed across your cluster based on different requirements, such as resource requirements or specific availability requirements, through the use of multiple availability zones. The instances within the Amazon ECS cluster also have a Docker daemon and an ECS agent installed, which communicate with each other, allowing Amazon ECS commands to be translated into Docker commands. Now let's learn about the Elastic Container Registry, also known as ECR. This service is closely linked to the previously discussed EC2 Container Service, as it provides a secure and centralized location to store, manage, distribute, and deploy your Docker images across your applications. ECR is a fully managed service, meaning that you do not need to provision any infrastructure to create this registry of Docker images, as it's all managed by AWS. Primarily designed for developers, ECR enables you to push, pull, and manage your library of Docker images in a secure and centralized location. To better understand this service, let's review its key components: registry, authorization token, repository, repository policy, and image. The ECR registry is the object that hosts and stores your Docker images, as well as creates image repositories. Upon creating your registry, you'll be given a default registry URL, where you need to replace with your own account information. Your account will have both read and write access by default to any images and repositories you create within the registry. However, access to your registry and images can be controlled via IAM policies and repository policies to ensure tighter security controls. As the Docker command line interface doesn't support different AWS authentication methods, before your Docker client can access your registry, it needs to be authenticated as an AWS user using an authorization token. To obtain the authorization token, you can run the get login command using the AWS CLI, as shown, where you need to replace the region text with your region information. AWS ECR get login, region, no include email. This will produce a Docker login command that you need to copy and paste into your Docker terminal to authenticate your client and associate a Docker CLI to your default registry. This process generates an authorization token that remains valid for 12 hours, after which you'll need to re-authenticate by following the same process. Repositories are objects within your registry that group and secure different Docker images. You can create multiple repositories within the registry to organize and manage your Docker images into different categories. By using policies from both IAM and repository policies, you can assign specific permissions to each repository, allowing certain users to perform specific actions, such as performing a push or pull. AWS offers 3 IAM managed policies to help you control access to ECR. Amazon EC2 Container Registry Full Access, Amazon EC2 Container Registry Power User, and Amazon EC2 Container Registry Read Only. For more information on IAM and policies, please click the pop-up banner now or the link in the description below. Repository policies are resource-based policies that require you to add a principal to the policy to determine who has access and what permissions they have. Once a user has access to the ECR authorization token API call, repository policies can control the actions that users can perform on each repository. Once you've configured your registry, repositories, and security controls and authenticated your Docker client with ECR, you can start storing your Docker images in the required repositories, ready to pull them down again as needed. To push an image into ECR, use the Docker push command, and to retrieve an image, use the Docker pull command. For more information on how to perform these actions, see the links on the screen. I'll put these links in the description below. That concludes this lecture on Elastic Container Registry. Let's now see what is Elastic Container Service for Kubernetes, commonly referred to as EKS. If you're new to Kubernetes, it is an open-source container orchestration tool designed to automate the deployment, scaling, and management of containerized applications, capable of handling tens, thousands, or even millions of containers. Kubernetes is also container runtime agnostic, meaning you can use it to run Rocket and Docker containers. For detailed information on Kubernetes, please click the pop-up banner now or the link in the description below. EKS is a managed service provided by AWS that allows you to run Kubernetes across your AWS infrastructure without having to manage the Kubernetes control plane, which is responsible for provisioning and running the infrastructure required for cluster management. You only need to provision and maintain the worker nodes. The Kubernetes control plane includes several components, such as APIs, kubelet processes, and the Kubernetes master, which enable communication between Kubernetes and your clusters. The control plane schedules containers onto nodes based on their declared compute requirements, tracks the state of all Kubernetes objects, and runs across master nodes. With EKS, AWS is responsible for provisioning, scaling, and managing the control plane by utilizing multiple availability zones for added resilience. In a Kubernetes cluster, nodes are worker machines running as an on-demand EC2 instance and managed by the Kubernetes control plane. For each node, a specific AMI is used to ensure that Docker and Kubelet, as well as the AWS IAM Authenticator for security controls, are installed. Customers are responsible for managing the worker nodes, which can connect to EKS using an endpoint. To start using the EKS service, you'll need to follow these steps. 1. Create an EKS service role. Before using EKS, configure and create an IAM service role that allows EKS to provision and configure specific resources. This role needs the Amazon EKS service policy and Amazon EKS cluster policy permissions policies attached, and only needs to be created once and used for all future EKS clusters. 2. Create an EKS cluster VPC. Using AWS CloudFormation, create and run a CloudFormation stack based on a YAML template. The downloadable YAML link has been provided in the description for you to copy. 3. Install kubectl and the AWS IAM Authenticator. Kubectl is a command line utility for Kubernetes that can be installed following the instructions provided on the screen now. https://kubernetes.io/docs/tasks/tools/. The IAM Authenticator is required to authenticate with the EKS cluster and can be downloaded based on your client OS, Linux, macOS, or Windows. 4. Create your EKS cluster. Use the EKS console to create your EKS cluster using the details and information from the VPC created in steps 1 and 2. 5. Configure kubectl for EKS. Use the update kubeconfig command via the AWS CLI to create a kubeconfig file for your EKS cluster. 6. Provision and configure worker nodes. Once your EKS cluster shows an active status, launch your worker nodes using CloudFormation based on a YAML template. The link to download the YAML template has been provided in the description. 7. Configure the worker node to join the EKS cluster. Download the YAML configuration map from the link given in the description. Edit and replace the ARN of instance role, not instance profile, with the node instance role value from step 6. Your EKS cluster and worker nodes are now configured and ready to deploy your applications with Kubernetes. Time for an AWS managed service that automates the deployment, provisioning, monitoring, and scaling of web applications. Also known as AWS Elastic Beanstalk. You can upload your application code and environment configurations to Elastic Beanstalk, which will then deploy and provision the necessary AWS resources, such as EC2, auto-scaling, application health monitoring, elastic load balancing, and capacity provisioning. This service simplifies deployment for engineers who lack AWS expertise. Elastic Beanstalk supports various platforms and programming languages and is free to use, but charges will apply for resources like EC2 instances. Elastic Beanstalk comprises several core components, including the application version, environment, environment configurations, environment tier, configuration template, platform, and applications. An application version refers to a deployable code section, which typically resides in S3 storage. An environment is an application version that has been deployed on AWS resources provisioned by Elastic Beanstalk. The environment configurations dictate the resources and their behavior in the environment, while the environment tier reflects how Elastic Beanstalk provisions resources based on the application's design. The configuration template is a baseline for creating a new environment configuration, while the platform comprises the operating system, programming language, server type, and Elastic Beanstalk components. An application can have multiple versions within a single application, and you can deploy the application across two environment tiers, the web server and worker tiers. The web server environment serves standard web applications over HTTP port 80 and typically uses Route 53, elastic load balancing, auto-scaling, EC2, and security groups. The worker environment is used for applications with a back-end processing task that interacts with AWS SQS and typically uses an SQS queue, an IAM service role, auto-scaling, and EC2. Elastic Beanstalk operates in 4 simple steps: create an application, upload the application version and additional configuration information, create the environment configuration, and create the environment with appropriate resources. Elastic Beanstalk will automatically update the environment to reflect changes in the configuration. Let's do some batch job now. AWS Batch is a service designed to manage and run batch computing workloads within AWS. Before delving deeper into the subject, let's clarify what batch computing is. It involves executing a series of jobs or tasks that require a vast amount of compute power across a cluster of resources. In non-cloud environments, maintaining and managing a batch computing system can be challenging due to the required software and resources that can be very costly. However, with AWS Batch, you can easily create a highly scalable cluster of resources that optimizes workload distribution and takes care of maintenance and management tasks. AWS Batch consists of 5 components:
Jobs,
Job definitions,
job queues,
Job scheduling.
Compute environments.
Jobs are units of work to be executed by AWS Batch, such as a Linux executable file or a shell script. Each job can have various states, such as submitted, pending, running, or failed. Job definitions dictate how a job will run, and with what configuration. For instance, they specify the number of vCPUs to use for the container, the data volume to be used, and the IAM role to be used to allow AWS Batch to communicate with other AWS services. Job queues hold scheduled jobs until they run, and multiple queues with different priorities can be used. Job scheduling controls when a job should run and from which compute environment. It typically operates on a first-in first-out basis, and higher priority queues are run first if all job dependencies are met. Compute environments contain compute resources to carry out jobs, and can be defined as managed or unmanaged. A managed environment is handled by AWS Batch, which takes care of provisioning, scaling, and termination based on the configuration parameters you enter. An unmanaged environment is created and maintained by you, allowing for greater customization but requiring more administration and maintenance tasks. If you need to run multiple jobs in parallel using batch computing, AWS Batch can be a perfect solution for tasks such as analyzing financial risk models, performing media transcoding, or engineering simulations. Up next in this video is Amazon Light Sale. This is a compute service that is similar to EC2 in many ways, but specifically designed for small-scale use cases. Light Sale is a virtual private server backed by AWS infrastructure, with fewer configurable steps than EC2 instances. Its ease of use and low cost make it ideal for hosting simple websites, blogs, and small applications. Multiple Light Sale instances can be run together, and they can even be connected to other AWS resources and your existing VPC via a peering connection. To deploy a Light Sale instance, all you need to do is go to the AWS console under the Compute category, or visit the AWS Light Sale homepage. From there, select Create Instance and choose your region and availability zone. You can then select your platform, Linux or Windows, and additional blueprint if needed. You can also add a launch script and choose an alternative key pair if necessary. Next, choose your instance plan, which determines the resources and monthly cost. You can customize each option to meet your needs. Once you've provided a unique name for your Light Sale instance and added key value tags, you can click Create Instance. Once your Amazon Light Sale instance is up and running, you can manage and monitor it easily. The Connect option allows you to connect to your instance using SSH, while Storage provides an overview of your current storage and lets you attach additional disks. The Metrics tab shows graphical metrics of your instance's CPU utilization, network in/out, and status check. The Networking tab lets you view your IP address information and control which ports your instance can accept connections from. Snapshots provides a simple way to back up your instance, while Tags help you filter and organize your resources. History provides simple order information, and the Delete tab lets you delete your instance when you're done with it. In summary, Amazon Light Sale is a cost-effective and user-friendly solution for small-scale projects and use cases. Its simple deployment process and easy management options make it a popular choice for hosting simple websites, small applications, and blogs. And that's a wrap on our overview of AWS Compute resources. Thank you for watching this video on AWS Compute brought to you by the Tech Think Tank. We hope you found this video informative and helpful. Don't forget to like and subscribe for more great content from the Tech Think Tank. If you have any questions or comments, please leave them below. Thanks again for tuning in, and we'll see you in the next video. Until next time, stay curious and keep exploring the world of technology.